The following video is on limits. How can we actually find the area of a circle? If we look at the following diagram, we see that we have a bunch of polygons inscribed inside of a circle. Since we know how to find the area of a polygon, what we can do is we can look at the size or the area of each of these polygons and look at what happens as the number of sides of the polygon goes to infinity. You can see as the number of sides of the polygon increases, the polygon gets closer and closer in shape and size to the circle. Another question that we're going to address is how can we find the speed that our car is going at a given moment? We know how to find the average velocity over a given interval of time. We do the change in the distance over the change in time. Or if s of t represents the distance that we've traveled at that time, t, then we can look at s of t1 minus s of t0 over t1 minus t0. The instantaneous velocity is how fast we're going at a given moment. In order to do this, we want to make the change in time as small as possible. So we look at s of t1 minus s of t0 over t1 minus t0 for values of t1 that are very close to t0. The solution to these questions is the concept of a limit. The notation is as follows. If f of x gets closer and closer to capital L as x gets closer and closer to little c from above and below, then we write the limit as x goes to c of f of x equals L. Once again, this is read as the limit as x goes to c of f of x equals L. For example, let's estimate the limit as x goes to 1 of x squared minus 1 over x minus 1. Notice that f of x equals x squared minus 1 over x minus 1 is not defined at x equals 1. That's because if we tried to plug in x equals 1, the denominator would be 0, and we know that makes the world explode and life bad. So let's create a chart, and we will plug in values that are very close to 1, but not equal to 1. So let's start with x equals 0.9. Using my calculator, I plugged in x equals 0.9 into f of x, and I ended up with 1.9. I did the same thing with 0.99, and I ended up with f of x is 1.99. Again, I used 0.0999, and I ended up with 1.999. I can also plug in values that are slightly bigger than 1. So 1.1 is slightly bigger than 1, but relatively close to 1. And when I plug it into f of x, I get 2.1. I can try 1.01, that's a little bit closer to 1. And when I plug it in, I get 2.01. I can also try 1.001, which is even closer to 1. And when I do that, I get 2.001 for f of x. So notice that in the first three columns, as x got closer and closer to 1, the y value got closer and closer to 2. Similarly, in the last three columns, as x got closer and closer to 1, y got closer and closer to 2. So we can write the limit as x goes to 1 of x squared minus 1 over x minus 1 equals 2. What did we mean when we said above and below? Remember in our statement of the notation of a limit, we said that f of x gets closer and closer to L as x gets closer and closer to c from above and below. What did we mean by that? Let's look at a number line. This is our x-axis, and somewhere on our x-axis we have the x value c. When I'm approaching from below, I mean that I'm choosing x values that are slightly less than c. So from below, or sometimes we'll say from the left, we mean that we're choosing values of x that are slightly less than c. We write this as the limit as x goes to c with a superscript negative sign on the c. This represents that we're choosing values of x that are slightly less than c. Similarly, we can approach from above c, and what we mean by that is we're choosing values of x that are slightly greater than c. So for this, we say that we're coming from above c, or sometimes we'll write from the right. And we write this as the limit as x goes to c with a superscript positive sign to indicate that we're approaching using values that are slightly bigger than c. F of x must approach L as x goes to c from both above and below in order for us to write the limit as x goes to c of f of x equals L. So in other words, we only say the limit as x goes to c of f of x equals L if the limit as x goes to c from below of f of x equals L and the limit as x goes to c from above of f of x equals L. Let's look at an example. The limit as x goes to 0 of the absolute value of x over x. Once again, we can create a table, and let's start by using values of x that are slightly less than 0. So this might include things like negative 0.1. When we plug in negative 0.1 into the function, we end up with negative 1 as the y value. We can try plugging in negative 0.01. When we do this, we get negative 1 as our y value. We can try negative 0.001, and once again we get negative 1 as our y value. So the limit as x goes to 0 from below of the absolute value of x over x is negative 1. We can do the same table, but this time choosing values of x that are slightly greater than 0. So like 0.1. When I plug that into my function, I end up with positive 1. If I try plugging in 0.01, I again get positive 1. And when I try plugging in 0.001, again I get positive 1. So the limit as x goes to 0 from above of the absolute value of x over x is positive 1. Since the limit as x goes to 0 from below and the limit as x goes to 0 from above are not equal, we say that the limit as x goes to 0 does not exist, or we write DNE. Let's look at another example. Let's estimate the limit as x goes to 2 of x squared. Once again, we can create our table, and we want to choose values of x that are getting closer and closer to 2. So let's try 2.1, and for that I plug it into my calculator and I get 4.41. If I try 2.01, which is slightly closer to 2, I end up with 4.0401. And if I try 2.001, which is even closer to 2, I get 4.004001. I can also try values of x that are less than 2. This might include things like 1.9. When I plug that into x squared, I get 3.61. If I wanted to get closer to 2, I could try 1.99, and I get 3.9601. And if I wanted to get even closer to 2, I could try 1.999, and I end up with 3.996001. So once again, I used a calculator for all these computations. The important thing to notice is that in the first three columns, x is getting closer and closer to 2. And we notice that as x gets closer to 2, the y value seems to be getting closer and closer to 4. In the last three columns, we notice the same thing. As x gets closer and closer to 2, y gets closer and closer to 4. So, the limit as x goes to 2 from above equals 4. The limit as x goes to 2 from below equals 4. And therefore, the limit as x goes to 2 of x squared equals 4.